Hello everyone, my name is Xiao from Indiana University. Today I will be presenting the paper OS-Aware Vulnerability Prioritization via Differential Severity Analysis. This is a joint work between University of Minnesota and Indiana University. I'm the first co-author with Qiushi. First, I will introduce some background information related to this topic and our motivation of this project. So with the limited maintenance results, the security engineer usually need to evaluate the vulnerability severity in order to prioritize patch. So given a vulnerability, how to evaluate the severity? So the common vulnerability scoring system, CVSS, is an open and well-adopted framework to evaluate the severity. The figure 1 shows an example of the Linux kernel evaluated by the CVSS system. So CVSS is a metric-based scoring system. The explorability metric have different vectors. For example, the privilege requirement metric describes the levels of the privileges the attacker must have in order to achieve a successful exploit. For each metric, there will be assigned a metric value. For example, here, PRH means that the attacker needs to acquire the higher privilege in order to lead to a successful attack. After each metric has been assigned a value, a CVSS score can be automatically calculated by the CVSS calculator. Hence, further, the severity of the vulnerability will be rated by the CVSS score. However, a fundamental problem arises in the one-for-all CVSS usage. When a bug reporter requests a common vulnerability exposure for a vulnerability, the CVE maintainer usually assigns one CVE number to the vulnerability with one single CVSS score. However, all affected versions or some derivatives will then simply honor the assigned CVSS score to perform the patch prioritization. An open source system tends to have a large number of derivatives. Take Linux as an example. There are at least 29 major Android systems running over like 24,000 models and billions of mobile devices. So why one-for-all CVSS usage is a critical issue? A vulnerability often have a different severity in a derivative system compared with it in the original system. Hence, the one-for-all usage vulnerability will result either underestimation or overestimation of the severity of the vulnerability. Specifically, if the severity of the vulnerability is underestimated, the patches for the severe vulnerabilities may be delayed or even ignored. When the severity of the vulnerability is overestimated, it will cause the delaying of the patching for more critical vulnerabilities when the maintainer results are limited. So in this paper, we propose an approach to determine if a CVE assigned vulnerability would have a different severity in the target OS. In this part, I will present the overview and the design of our approach. Our approach is a combination of the programming analysis and the natural language processing techniques. Specifically, we take a CVE, Linux mainline, and a target Android kernel as our inputs, and we will output whether the CVE is less severe or more severe in the target OS. I will detail the major steps in the next few slides. Before that, I will give you a quick example showing the high-level insights of our approach. Let's take the CVE 2016-2085 as an example. The left side of this slide showing the vulnerability call chain in the Linux, which takes the system call as the entry point and vulnerable function as the endpoint. The left side of the slide shows the right side of the slide showing the vulnerability call chain in the Android kernel. The function in node permission is a differential function which appear in the core chain in Android kernel, but not in the core chain in the Linux kernel. Based on the description of this function, check for the access rate for a given node. We can reason that this function requires the attacker to have a higher permission to lead to a successful attack. Hence, the privilege requirement metric will be high. Compared with the original metric in the Linux kernel, PR_num, we can conclude that the attack needs to achieve a higher privilege in order to successfully exploit the vulnerable component in Android kernel. That means this vulnerability in Android kernel is less severe than that in the Linux kernel. As we can see, if we can obtain the differential functions between two core chains in the different operating system, and if we also know the vulnerability exploitability metrics related to the differential functions, then we can perform differential analysis of the severity of the vulnerability in the different operating system. But the challenge is, how can we identify the vulnerable core chain and reason the exploitability metric of the different functions? To identify the vulnerability core chains, we first extract some semantic information of the vulnerability paths from the CVE and git log description. Those information will further help us to rebuild the vulnerable core chain in the target system. For example, the extracted vulnerable component-related info like the system call and vulnerable function will serve as the entry point and endpoint when we construct the core chain in the system. To rebuild the core chain, for example, in the Linux kernel, we first compile the Linux kernel, then we generate a Linux core chain, and after that, we're using the semantic information to select the most possible exploitable core chain in the Linux kernel. Similarly, we also rebuild the core chain in the Android kernel. So here, metric to function mapping will construct a map between the function and the exploitability metric. To automatically construct this map, we trained a bio-LSTM model with the attention mechanism for the function description reasoning and exploitability metric classification. Okay. After we obtain the core chain, we can compile the two core chain and we can obtain the different functions. And then we can using the metric to function map to get the different exploitability metric. Further, those different exploitability metrics will be used to prioritize patch. In this part, I will present the evaluation and results of our approach. Based on the differential severity analysis, our tool can output the metric level difference. The results are summarized in the table 7. Furthermore, our study also measures the score level difference. As we can see, the majority of the vulnerability have the different severity score in the different operating system. Specifically, 72% of the vulnerability are more severe in Linux than Android, which means that prioritizing the patch for those vulnerabilities in Android may waste the maintenance resources which are supposed to be allocated for the critical vulnerabilities. 15% of the vulnerabilities are more severe in Android, which means that those vulnerabilities may not be patched timely in Android if the severity evaluation is just based on the CVSS score evaluated in the Linux kernel. We further conduct a user study to evaluate the usability of DIFFCVSS from the user perspectives. We recruited 10 downstream maintainers in the industry who have the real-world experience in the vulnerability evaluation, and 20 graduate students who have a background in the security system security analysis. As we can see, with the help of the tool, the average re-evaluation time is around 27 minutes, which is much less than 4.8 hours without the tool. Our results also show that DIFFCVSS can significantly reduce the time and efforts for the vulnerability re-evaluation. Besides, our tool can also achieve like around 19% of the accuracy in both metric level and the severity level. Conclusions. So, one-for-all CVSS usage will cause critical issues, which will cause either over or underestimation of the severity. And our tool can determine if a vulnerability have a higher or lower severity in the targeted operating system and avoiding the over and underestimation. And the results showing that the majority of the vulnerability will have a different severity in the different operating system, like Linux and Android. And even with in the different versions of the Linux, the result, the detail of the result are in the paper. If you are interested, you can check the results. That's it. Thanks for listening. We are here for questions.